Let's record this. And all right, class. So we are now recording the second session for week 2. We left off with this ideal situations in linear regressions where the error term of all the independent observations is 0. So this is the ideal model within the Gauss-Markov theorem. So there are, of course, different observations that we can see. Trying to get this minimized. So these are the different scenarios in our experiment. You have the first one on the left is when there are 0, the error term of all the independent observations is equal to 0. And here you see some errors in your observations in some of your group of your independent variables. And then this is a representation of a homogeneous errors. And so this is what we call, it meets the assumption of the linear regression OLS, ordinary least squares, which is the homoscedasticity of the variance, which means that there is homogeneity of the variance among the different groups of your independent variables. On the right side is you see that the big blue, I would say, data representation here on the slides. You see that there is heteroscedasticity, which means that there is non-homogeneous error or non-homogeneity of the variance. And it happens when there are outliers, and the homoscedasticity is represented when there's no outliers in your sample, in your independent observations of the different groupings of your study samples. Can I request to mute your microphone again, because I hear a lot of echo and noise? Okay, thank you. All right, so this again is the homogeneity or homoscedasticity. This is on the right side of the slides, is the heteroscedasticity or non-homogeneity of the variance of the different groups in your sample population. And it's best represented by this 2 when there's no outliers and when there are outliers. So it's important to examine your data before you do your linear regression analysis, because you need to make sure that the assumption of, which is represented by the left graph, the homoscedasticity of the variance of the groups is met. And that's exactly the same as, remember I mentioned ANOVA. The test for the assumption of homogeneity of the variance is right here, is the Levene's test. It's one of the SPSS output that we always need to check when we are doing ANOVA. So there's a lot of similarities of the underpinnings of ANOVA and regressions. And then the other thing that you can do by looking at your skewness and by looking at assumptions of normality. So actually I have a prepared here. I just did an analysis for one of my students. The pre-test mean score and the patient, my student is using the paired t-test, and just like ANOVA is for 3 groups, this is an analysis of 2 groups only, so what we call the 2-group ANOVA, or what we call the paired t-test. And in the pre-test score, the skewness is minus 0.417, and in the post-test, the skewness is 0.02. So remember that it's normally distributed because the skewness should be 0. So as soon as you have higher number other than 0, whether it's positive or negative, so this pretest score in the sample, you can also see this right away by looking at your histogram with the normal curve distribution, which is represented by the bell curve. So as you can see here in the pretest, because the skewness value is minus 0.4, you can see that it doesn't look like a perfect bell shape. Like you will look at the bell, it is slightly skewed to the left, which is negative skewness or left skewed. And whereas the post-test, which has a skewness of 0.04, you can see here the bell curve is looking more normal. It looks like a bell shape. And the best thing to really examine the histogram with normal curve distribution is to always cut it into half. You look at the tip of the curve, and when you cut it, each of the halves should be a mirror of each other. So that's just your visual examination right away, whether your data is normally distributed or whether it's a skewed data, which is a test of homogeneity of the variance. So again, look at this bell. This bell right here looks flatter, and so slightly skewed to the left, as you can see here, because it has a minus 0.4 skewness value. So these are very important concepts when we look at ANOVA, when we look at OLS. You definitely need to make sure that the assumptions are met. So just like ANOVA, OLS, or ordinary least squares, has assumptions that must be checked, or what we call control. We need to control in order to get the best linear unbiased estimator, or BLUE. Okay. All right. So right now, I'd like to know if there's question from the group, from any student. Siti, do you have any question?
Excuse me, Doc, I would just like to ask, where does the outlier came from?
Oh, from your observation, it could happen. Remember that the outlier could be really one of your respondents in your sample, or it could be an error when you input the data to SPSS. So that's why you need to make sure you check that, because human errors in data imputation or data transfer from your questionnaire to SPSS, outliers are due to errors. Likely it's in a normally distributed when our model assume that there is normal distribution, every time we look at outliers, we always have to think, is this really an error? Just like intelligence, the outliers are the genius. Just like when it comes to income, we don't want to put the income of Bill Gates, because if Bill Gates will be one of our respondents for income, and that's our independent variable, and he has 40 billion in asset and his income is X million a year, and then we look at income as a predictor for success in college education, we are in trouble. We have an outlier if so. That's why we need to make sure that those, when you are doing surveys, it's the responses. We need to check that the responses, that there are no outliers. When we do experiments, we make sure that we don't have error in measurements, that our machine did not break down and did not give us really extreme results. There are errors in our data imputations. And again, all of these errors, we try to control them, and we try to always check. That's why we check all these assumptions, or else we will not get our relationship, our best estimation of the relationships of the variables. We will not get the best predictive power of our predictive analysis using the model. So it's very important that we look at all of this. So just like what I did with my students right here, I'll show you.
So, excuse me, Doc, when you say outliers, it normally, what do you call this? It means that the data set that you have, if it implies any error, then you have to revise everything.
Not
Or
necessarily.
only within your data.
You just, yeah,
The data that you have gathered, or
correct. No, it's just means that you need to control these outliers, and you try to make an analysis by removing these outliers so that you have a best representation. So yeah, we need to, you as a researcher, and statisticians will always do this, when they see outliers, they remove the outliers and they look at the results again. Is it statistically significant when by the time you remove the outliers? No, it's us, the researchers. We need to control, and we need to always clean our data, but it doesn't mean we hide them. We just, we make different statistical analysis, two sets of statistical analysis, removing the outliers and not removing the outliers, and see what happened to the statistical significance of your experiment. Because we have to really make sure that those are not, that, because outliers always almost represents error in measurement, unless they are a true value of your data. Just like, you happen to really include Bill Gates and Warren Buffett in your respondents, and so you really have to remove them in your analysis, because these are outliers, and they might make your analysis not statistically significant, because there are 2 or 3 outliers in your, that are really extreme values from all of your observations. So that's why those assumptions are there. Those assumptions of homoskedasticity and those assumptions of normal distribution are all there, because in the real world, those are really extreme, right? I mean, Warren Buffett and Bill Gates are, and their income are extremes. So the same thing when we look at a phenomenon of interest. We look at the data that we collected and we make sure we don't have these extreme values that might really not give us the best predictive power, the best association, best relationships of this independent and dependent variable. All right, any other questions from the group?
Doc, I would just like to ask regarding the heteroscedasticity and homoscedasticity.
Homoskedasticity, yes, I have a hard time pronouncing them too. So,
in relation to that, Doc, but how do you and how do you do the interpretation in that when research is involved?
okay, so those are assumptions that you and the statistician must always make sure that you check before you present your analytic results or your data, your final results. So how do you determine? By examining your data sets. So again, the two ways to do that is you look at normal distribution, you look at your skewness statistics, you look at, which is, you know, when we did before, we have the skewness is 0 is always, there's no skewness, and anything that's minus or negative is skewed to the left or negative, and then positive skewness, higher values, if this is 0.5, 0.6, and remember 0 is normal or no skewness. So that's one. The second one is we do the Levene's tests, and then the normal, I'm looking at your, again, the histogram with normal curve distribution, because they have to be normally distributed. That's how you know that it's homoskedastic. When there is heteroskedasticity, what that really means is basically, is it skewed to the right or skewed to the left? And when we look at here in the logistic regression, I mean, not logistic, but linear regression. Remember, logistic is only when the dependent variable is 2, which we will cover later on. Logistic, the word logistic is very appealing because it's for when the dependent variable is dichotomous only. So which means, like, especially in epidemiology, if the disease, no disease. So that's, it's very appealing to do logistic regression all the time, because there's a lot of our questions in research that are just dichotomous dependent variable. It can only go 2 ways, yes or no, disease or no disease. And so right here, it's the same thing with this model. It's basically that we are looking at homoskedasticity. It's looking at skewness to the left, and which is where you have a lot of error terms in your beta or y-axis, and you have a lot of error terms in your x-axis. So there's more independent observations that falls below the line, and so that can be interpreted as right skewness. So these are really visual comparison when you look at the terms are very fancy, but it goes back to the simple understanding that are the data skewed to the right, skewed to the left, and therefore they are not normally distributed, and therefore there's no homogeneity of the variance of the group, and therefore it is a heteroskedastic data and or non-homogeneous observation. So Is it clearer visually?
Yes, doc. Yes.
Very good. Okay. For me too, I was so confused when I was a student, but then when we have group discussions, it's so nice to have the perspective of the understanding of your classmates, because it really clicks to me right away. It's like, yeah, I mean, it's like we are taught with this so many different terms, but there's really a universal theme in statistics. Whether you use descriptive statistics, whether you use ANOVA, whether you use regressions, it's this universal themes, universal underpinnings. It's consistent. It's there all the time. We just need to connect the dot, because sometimes we as what Dr. The one that I admire the most, the author of this modern regressions. It's in our one of our readings. Who's the dean of the graduate school of Clemson University, Dr. Osborne, and he's really my role model in statistics, and I've learned a lot by reading his book, and I got a better understanding of what is this ANOVA, what is this regression, and so by reading his 2017 latest edition of his regression analysis book, I really have a better understanding that there are many universal underpinnings of ANOVA and regressions, and even again the underpinnings of descriptive statistics under normal distributions, such as your t-test that assume normal distribution. All of that, you have to make a unified understanding, and it's much easier instead of like putting a compartment. It's like modern statistics is really in one of his nerdy manifesto, he really emphasized that we cannot teach our student to be ANOVA researchers, and we cannot teach our students as regression researchers, but rather our students should always look at all of this statistical analysis as universal, and should look at the universal underpinnings of these different statistics, and then use the statistics, that there is no right or wrong statistics as long as you appropriately model your research question with these different statistical analytic procedures. All right, so I think I've covered those. I've really emphasized normal distribution, checking the skewness, and for linear regression, it's looking at, again, homoskedasticity versus heteroskedasticity. And I have demonstrated that in ANOVA, we look at the Levene's test, and if they don't, and right here, the statement of Levene's test is very simple, that it should be not significant, because if it's statistically significant, then we reject the null hypothesis that there is homogeneity of the variance. Therefore, it's heteroskedastic or non-homogeneous, which violates the assumption of ANOVA. So we do Levene's test, and if that is, again, if this Levene's test in our ANOVA output is statistically significant, we use Kroskal-Wallis, because that Kroskal-Wallis will correct all those errors in the measurement. Okay, and so what else I'd like to emphasize? So good. I think I've said what I really like to emphasize, and I'd like all of you who will finish this course to have that universal view of the different statistics, and not to become sort of like, one camp over the other camp. All right, so I think we can breeze through with this, with correlation statistics. It's 9:26. I know I need to be done before 9:40 because this is only a 40-minute video again. So let's breeze through this. So what are correlation coefficient? These are the different, this correlation is indicating in layman's term as association. It is concerned with specific type of relationship, and it's measured mathematically, and that the coefficient is a measure of the strength and direction of the relationship between your independent and your dependent variable, and that the p-value is the calculated statistics, or the test statistics value, which provide an assessment of how significant is that association of between the independent and dependent variables. Two types of correlation coefficient that's commonly used in nursing research is the Pearson and the Spearman. Pearson is parametric, Spearman is non-parametric. And the feature, you need to use Pearson correlation when your variables, your independent and dependent variables, are at the interval or ratio scale level of data. And you use Spearman correlation if it's a non-parametric, which means not normally distributed, and non-parametric, remember, is that it doesn't have the features or characteristics of a parameters. And what are the parameters? The means, the medians, and the modes. And so when you have a non-parametric assumptions, it's important to use your Spearman correlation. And this is so important that when you have ordinals, such as those Likert type questionnaires, those are ordinal type of data. They are not interval, which means that the distance between one value is exactly the same with the other distances in different levels, or ratio, which has the highest level of measurements, which is a natural 0 point. So again, I have seen a lot where Likert type scale, where Likert type scale is used in research, and then they will get the mean score of the Likert scale. For example, if you're measuring the severity of fatigue, but it's a Likert scale, then you know that you cannot use Pearson correlation coefficient, because Likert type scale produces ordinal data, and it is at ordinal level of measurement, and therefore you need to use Spearman correlation if you're interested in looking at the relationship of cancer-related fatigue measured by a Likert type scale that's reported by the patient, and its relationship to sleep disturbances, for example. And so that is really an important thing to remember. So Pearson versus Spearman. Make sure that you use the appropriate one. And then this is our hypothesis. It's very simple. There is no correlation between the two variables. That's the null hypothesis. And there is correlation between the two variables, which is your alternative hypothesis. And then the next question, the next slide is that it measures that correlations measures the strength and direction. And it's denoted by R. And so correlation coefficient, whether it's Spearman or whether it's Pearson, is denoted by R and can fall between -1 and +1. -1 means perfect negative or inverse correlation between the variables. And +1 means a perfect positive correlation or relationship. And so basically what a positive correlation represents is that when one variable increases, the other variable also increases. So that is positive. Whereas the negative correlation is that when one variable increases, the other decreases. That's a negative correlation. And when there's no relationship, the R is 0, which means that there's no association between your independent and your dependent variable. So in summary, the closer the correlation coefficient is to 0, the weaker is the association between your independent and your dependent variable. And it can be represented by this diagram of your A, which is your independent variable, and your B, which is your dependent variable, and how closely related they are. And this Venn diagram shows you that the shaded area is the shared variance, or what we call the square of, or R squared, which is the shared variance between variables A and variables B, which is your A is your independent variable and B is your dependent variable. And the clear area shows the unique variance of each variable. So here is a scatter plot of a study that did not have any correlation, that showed no correlation, which has an R of 0 between independent variable and dependent variable. So you can see they are not remember we just went through OLS and linear regression. And so you have your beta and your alpha. You just imagine again, if you're using OLS or linear regression, simple linear regression, you can really visualize here that you have your beta and you have your alpha, and then the line represents your coefficient or your intercepts. And so that is, the line determines slopes or intercepts, and that's your coefficient. So this is basically your R. And this is a study that did not show any correlation between independent and dependent variable. And look at these observations. They are not tighter. They are not in, they're not pooling, maybe is the right word. These observations are not, they're not pooling or pooled. Of this, the pooled observations are not in alignment with this linear model, which is a straight line, and between the alpha and the beta of your model. And then right here you can see that the observations are really scattered and evenly. The correct word is evenly scattered to the y-axis and the x-axis. And if we are using the linear regression model, it's the beta and the alpha. Okay, so the next slide is showing you that if your observations are group or pulling towards the line, and then as the independent variable increases, the dependent variable also increases. So that's perfect positive correlation of these two variables. And then here, the negative correlations is exactly the opposite visualization of that line. And that is this perfect negative correlation, is that as the one variable increases, so right here, so your independent variable increases, the dependent variable decreases. And so that is a perfect negative correlation. So increase, the other one decreases, perfect negative correlation. When one variable increases, the other variable, the dependent variable, also increases. That is your perfect positive correlation. So what are the types of research that can answer correlations? Well, these are, if you're really interested at relationship, examining relationship, that's when you use correlation coefficients. Again, it depends whether your assumption is parametric or non-parametric, and your type of data. So remember, when you met the relationship of theory and measurement. So it's so important to always remember theory and measurement. And I sent you that as a foundational reading. That was an editorial by Dr. Lee Smith, that he really emphasized the importance of the theory and measurement. And so what is it that you measure? So if the measurement is really is a Likert type measurement, so you produce the data that is ordinal, and so that's the theoretical assumption of that data. So you need to use the appropriate research. So research and statistics, the relationship of these two, and then you have to put these pieces together, and then you do your computing using SPSS or other statistical software. So these are Pearson correlation and Spearman correlation differences. We already covered all of this. And again, if it's non-parametric, you use Spearman. If it's ordinal, you have to use Spearman, such as all of your Likert type questionnaires that collect ordinal type of data. Variables need not be normally distributed, and the two variables are related to each other, could be in a monotonic way, but it does not change, but not necessarily a linear in relationship. And then this Spearman correlation also is highly applicable to analysis if there are outliers, some outliers, because the Spearman test is less influenced by outliers. So that's why we need to examine our data. That's why we always do scatter plots. We do normal, we do histograms with normal curve distribution to have visualization of the data. We also do QQ plots. Actually, I think I have not covered QQ plots in statistic 1, but that is another visual representation whether your data is normally distributed. All right, so it's 9:39. I probably have another just 2 minutes. We already know the different steps to do this, and I'm just gonna breeze through all of that. And again, we already cover this basic 6 steps in our statistics 1, so I'm just gonna skip that one. And then here's your correlation coefficient that's represented by R. And again, correlation, the R squared right here, and right